Hi everyone, it's your boy David from dodnatic. So in this video we'll see what an equivalent circuit is, and we're going to talk about Norton's and Thevenin's equivalent circuits. And also we'll get some times to do practical examples so that we can get a better and deeper understanding of those theorems. Let's get in motion. So I wanted to talk first about what an equivalent circuit is. An equivalent circuit is just a different form of a circuit that behaves the same and retains the same electrical characteristics as the original one, but is simpler in terms of the parts or in terms of the components it has. So the word equivalent here actually refers to the fact that we can still produce the same electrical properties as like voltage or current when viewed from a specific pair of terminals or ports with a simpler circuit. So these kind of equivalent circuits are really useful because they allow us to put the focus on a single portion of a circuit instead of the whole thing when analyzing or troubleshooting circuits. So let's talk about Thevenin equivalent circuit. The Thevenin circuit only contains two values: a voltage source and a resistor connected in series. So this tells us that we can replace any linear circuit network with only two components, the Thevenin equivalent voltage and the Thevenin equivalent resistor. So our goal is to find those values that are the ones that will be seen between point A and B where external connections are made or when you connect your load in the original circuit. To do this, we're going to follow some steps. Step 1. We're going to let the connections between point A and B in open circuit so that we can perform any circuit analysis method to calculate the voltage between those 2 points. Step 2. We're going to short circuit all the voltage and current sources, and we're going to calculate what is the resistance between the point A and B. And finally, step 3, the easier one, is just to draw your equivalent circuit. You already have your voltage value and you have your resistor value. So now you can perform any calculation in an easier way. So with this information, I think we need to make a real example so that we can get a better understanding of this theorem. So we have a Wisdom bridge here, and we want to calculate what's the voltage across the 47 ohm resistor and the current through that resistor. So we're going to use Thevenin's equivalent circuit to replace the whole thing and just focus on the single RL resistor. So step 1, we're going to make an open circuit between A and B, and we're going to calculate the voltage across the 2 points. So if we take a closer look, you can see that basically we have like 2 voltage divider networks. So we're going to calculate voltage A and voltage B using the voltage divider equation. So we have that for point A, the voltage is equal to 9 times 470 over 470 plus 220. And that gives me 6.13 volts. So for point B, we have that the voltage is going to be equal to 9 volts times 100 over 100 plus 220, and we have a voltage of 2.81 volts. Okay, so remember that the voltage is a difference between 2 points, so we have that the voltage between A and B is equal to 3.32 volts, and this is our Thevenin's voltage. Step 2. Now that we have the voltage, it's time to find the Thevenin's resistor. So we're going to short circuit all the voltage sources, and we're going to calculate the resistance. So basically we have 2 branches of resistor in series, and they are connected in parallel. So first we're going to resolve the resistor in series. So R1 plus R2 is going to give me 690, and R3 plus R4 is going to give me 220 plus 100 equal to 320 ohms. And finally, we're going to use the parallel equation. And we're going to have that the Thevenin resistor is equal to 218.6 ohms. Our third step here is just to draw our Thevenin's equivalent circuit. We already have the voltage and the resistance, and we're going to put in series the low resistor 47 ohms. This way we can perform any calculation in an easier and simpler way. So we're going to start by finding the current through that resistor. Since both of the resistors are connected in series, we already know that the current is the same in both of them. So we'll have that the current is equal to the voltage over the full resistance of the circuit. So we have 218.6 plus 47 ohms, and this gives me a current of 12.5 milliamps. Now that we have the current, it's just very easy to find the voltage. So we have that the voltage, according to Ohm's law, is equal to the current times the resistance. And this gives me a voltage of 587 millivolts for the single low resistor. Okay, so let's see the circuit on a breadboard, and we're going to measure the voltage to see how close we are. Alright, so I wanted to test to see if the theory it's good enough to, get really close to real practical values. So in this case, I have replicated the circuit into my breadboard. I have the same resistors, and I have my 47 ohm resistor, the low resistor. So I'm going to be measuring the voltage across the low resistor to see, what we get. So the first time, this is really impressive. The value, it's almost the same. It's very close, like around 550 millivolts. So let's try one more time to see if the value remains. So the second time the value is lower. This time is around 440 millivolts or something like that. But this is because the battery, since it's like connected directly without any kind of switch or something, is discharging all the time, so the voltage is decreasing. But we can see that the values are really close, and this theory is very nice. Norton's equivalent circuit. So the Norton's proposal was quite similar to Thevenin's. However, in this case, we're going to use a current source and a resistor connected in parallel. So once again, I have resumed the steps to find these values in 3 steps. The first one, we're going to set a shortcut between point A and B where external connections are made, and we're going to calculate the current flowing through that branch, and that is going to be a Norton's current. Step 2, we're going to set a shortcut for all the voltage sources and all the current sources, and we're going to calculate the whole resistance between point A and B. And finally, but not least, with the values that we have, we're going to draw our equivalent circuit. Awesome. So I think that we have the knowledge to go through this steps, but with a real exam. So let's do it. Okay, so this is the circuit that I have, where we're going to be using Norton's equivalent circuit to find the current through the resistor RL and the voltage across the resistor RL. So the first step is that we're going to be finding the Norton's current. To do this, we need to set a short circuit between point A and B and find the current going through that branch. But if you see the circuit, it's not that easy because it's kind of complex. So first I'm going to find the voltage that I have labeled as V1, and I think KVL is very handy to do that. So we have that the V1 is equal to 5 volts plus 47 ohms times 50 milliamps, and that gives me 7.35 volts. So with this voltage, I can redraw the circuit that I need, and with the resistor of 220 ohms and the 100 resistor. Having this, we see that this is like a 2 resistor in series, so we can simplify this circuit even more. with a 320 ohms resistor. With this simpler circuit, now we can calculate what's the current going through from A to B, and this is the current going through the whole circuit. So using Ohm's law, we have that the current through the circuit is equal to 7.35 volts over 320 ohms. So this gives me a current of 23 milliamps, like approximately 23 milliamps. Okay, so that's our Norton's current. Now the step 2 is to find the Norton's resistance. So to do that, we need to short circuit the voltage sources, and we need to let an open circuit for the current sources. And this is basically how we look if we do that. So we have resistors arrangement here, and we need to know what's the equivalent resistance for the whole circuit. So basically we have these two first resistors in series, the 47 resistor and the 220 ohms resistor. And the second one is in parallel with these two. So the whole resistance here is equal to 75.75 ohms. So step 3, now that we have all the Norton's value, let's just, try out the equivalent circuit. So we have our current source of 23 milliamps, and we have our parallel resistor of 75.75 ohms. So this way we can just connect our load resistor 1k ohms and perform any calculation in a very simple way. So we're going to find what's the voltage across this resistor. So we have that the current is 23 milliamps, and the voltage according to Ohm's law, it's current times resistance. So we have 23 milliamps times 75.75 ohms, and that gives me a voltage of 1.74. And for the current, we have that the current is equal to voltage over resistance. So the current across that resistor in this case is equal to 1.7 milliamps. My bad for that mistake. Unfortunately for this circuit, I couldn't replicate it, but I'll be using a simulation to test Norton's equivalent circuit. Okay, so I have set up my simulation. This is the original circuit. So in the previous example, we found out that the voltage across the 1k ohm resistor was, 1.74 volts, and the current across the resistor was 1.7 milliamps. For this case, checking the simulation, we have the green line, and this tells us that the voltage is equal to around 1.8 volts, and the current is around 1.8 milliamps. So this is really close to the example, so that's very cool. Hey, I appreciate you've come to the end of the video. I really hope you learned something today, or if you just enjoyed the video, please let me know by clicking on the like button, or I'm not getting mad if you're subscribing. Alright, so that's a wrap. Once again, it's David from dodnatic, and I'll see you in the next one.